proposed a low latency multi-channel speech enhancement system for hearing aids, which we call it LLM-MSE. Let's start with the challenging scenario. The key points of CEC is to improve speech in the presence of background noise. With the situation that a listener listening to a target speaker in a room, while 2 or 3 interfering sound sources are also active. The scenes are described by a large number of randomized parameters, like room size, materials, geometry, and so on. For the receiver, it has 6 microphones, so that we have 6-channel noisy signals as inputs. Head rotation information is provided also to better locate the angle of the talker. The evaluation of system is divided into 2 parts to maximize HSP intelligibility score in objective evaluation and provide hearing impairments for listeners to maximize their hearing test scores in subjective evaluation. Okay, this is our provided system's overall diagram. It can be divided into 3 main parts: a denoising module, a beamforming module, and an application module. We also proposed an asymmetric window pair to achieve high frequency resolution while maintaining low latency. Moreover, there are encoder and decoder at the start and end of the network, which can refine the spectrogram of different frequency points and channels. The denoising module is a single-channel speech enhancement in magnitude domain, while the beamforming module can be regarded as a multi-channel speech enhancement in complex domain. And the amplification module provides hearing empowerment by different autograms in magnitude domain. The reason why we designed this will be explained immediately. Let's start with our proposed symmetric window pair. The shape of the window pair is shown in the diagram B. It can achieve a high frequency resolution while still maintaining a low reconstruction latency. Compared with other commonly used symmetric window pairs, our proposed asymmetric window pair have a different shape of forward window and backward window. We set front part of the backward window to 0, and the function of the asymmetric window pair is posted here too. Let's take a window size equals to 4 times hop size as an example. As we can see from the reconstruction diagram, the inverse STFT will overlap at the 4 frames information to get the final output. The asymmetric window only relies on the first 2 frames because the signals for the 3rd and 4th frames are all 0. So we can reconstruct the signals when we have the first 2 frames only, so that the final algorithm latency will be 2 times the hop size. In this way, we set the window size to 16 milliseconds and the hop size to 2 milliseconds. Then the overall latency will be 4 milliseconds, and it meets the challenges latency requirements. Let's go back to the network architecture and start with the spectrum feature encoder and decoder. The only difference between encoder and decoder is that the encoder is 6-channel in, 6-channel out, while the decoder is 6-channel in, 1-channel out, as the final output will be a 1-channel signal. There is a conv2D for high-dimensional information extraction, and a dilated dense block to capture long-term contextual information, and another conv2D to decrease dimensions and extract local features. Layer norm and period rule are inserted after each convolution operation for better performance. Yeah, the next is our denoising module. We decoupled outputs of encoder into magnitude and phase, and only use the magnitude information, leaving the phase unchanged, because the beamforming process is sensitive to phase. Moreover, the channel dimension is transferred into batch to reduce interference between phases, so that it can be regarded as a single channel model in magnitude domain. The architecture of this module is a convolutional encoder-decoder topology with kernel size of 3 in frequency dimension and 2 in time dimension. The channel size of each encoder and decoder is set to 16.4. After the denoising module, the 6-channel outputs will concat with the heterotation information and fed into the beamforming module. There are 2 main parts for beamforming module, the subband module and the full-band module. The subband module will model the low-frequency points and high-frequency points separately, while the full-band module receives both the output of subband module and the original spectrogram as inputs, and refines the certain unsmooth connections at the boundary of low frequency and high frequency, which is introduced by the subband module. Let's say more about the architecture of subband module and the full-band module separately. The full-band module just uses a complex conv2D with kernel size of 3 in frequency dimension and 2 in time dimension. The subband module will take a complex group convolution with group size 2, so that it can model the low frequency points and high frequency points separately. Also, the incidence norm and the period rule are added after each convolution operation. The final stage of the network is the amplification module. We designed 2 different amplification models for objective evaluation and subjective evaluation separately. For the objective evaluation stage, we use a neural network which is the same as the denoising module, and a differentiable Husky loss function is used to train it. For the subjective evaluation, we developed a wide dynamic range compression algorithm to compensate hearing loss for different hearing impaired listeners. And the WDRC algorithm is tuned by the Sennheiser PCX headset, which is used for hearing tests in the subjective evaluation stage. As for the datasets, the challenge organizer provides 6,000 scenes with 24 different speakers. And we generate 20 more different situations with different interference and SR settings. The development set and the evaluation sets are also provided by the challenge organizer. For the listener data, the training data set consists of 100 audiograms. We also randomly generated some other audiograms to avoid overfitting. The evaluation set consists of 15 audiograms, while the final listeners have 25 to 16 decibel hearing loss in the beta ear. In the training stage, the silence frame are removed by the provided datasets labels to make the model focus on denoising. All signals are resampled to 32 kHz after feeding to the network. And the training process are divided into 2 parts. Firstly, the denoising module and the beamforming module are trained using channel 1 of target signals, not the anechoical signals, as we found that the anechoical signals have a little misalignments with the noisy signals. After this, the model is loaded as a pre-trained model, and the implication module is added to train the final model. As for the loss function, we use CSR loss for the first stage and the differentiable Husky loss for the second stage. Our model has 7 million training parameters, which requires approximately 18.6 G-flops. As shown in the table, our proposed system significantly outperforms the baseline system in the development stats, with an average Husky score of 0.7673. The result of the subjective evaluation has not been published, so we posted 2 demos to show our system's performance. As shown in the spectrogram, after training stage 1, the denoised signal seems to be very clean compared with the noisy signal. And our WDRC algorithm will amplify the denoised signal based on audiograms. Okay, in this work, we proposed a multi-stage and multi-channel or neural network hearing aid system, which significantly outperforms the other traditional approaches. We also proposed an asymmetric window pair to achieve high-frequency resolution while maintaining low reconstruction latency. However, we found that a traditional WDRC algorithm still performs better in subjective evaluation stage. In the future, we will also enable the proposed system in more complicated environments and decrease computational complexity. Okay, that's all. Thank you. Any questions?